Hi, welcome to AB Video 3.78 Part 1, Introduction to Optimization Problems. Okay, so this is 3.7. They're basically word problems, application problems. Optimization means we're looking for maxes and mins. So one of the things you're going to want to notice about all these problems, maximum, they want the product to be a maximum, the sum is the minimum, they want the product, the sum of the first and blah, blah, blah is a minimum, 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 maximum. What gives the maximum area, what produces the minimum perimeter. Closest means minimum distance. Least amount of paper. So you're going to have to pick out the noun or the adjective that implies a maximum or minimum. Greatest, maximize the flow rate. What dimensions will require the least amount of fencing so that the area will be a maximum. They want a maximum volume. Here they want a maximum area, etc. So they're not going to tell you, hey, by the way, this is an optimization problem. It's going to be up to you to realize they're looking for a max or they're looking for a min. Okay, so the first thing you're going to have to do is come up with an equation, a function in two variables. Now, of course, we're only dealing with two-dimensional. We're not dealing with 3D, so you've got to get it down to two and only two variables. Normally, you're thinking y and x. However, it's going to be easier if you use letters that represent what you're looking for. Now, whatever you're asked to maximize or minimize is going to be your y, and I'm putting that in quotes. So, for example, if they ask for the minimum cost, you want a function c of x equals, and it could be a different variable here. I'm just saying x. If you want a maximum area, it would be a of x. If the only other dimension you have is radius, it would be the area as a function of the radius. The domain is also going to be interesting here. You're going to look at the algebraic domain. You can't have a denominator of 0. You can't take the square root of a negative, etc. However, we're also going to have a real-world domain. There are many things that will not be negative, like the length of the side of a rectangle or the radius of a circular base. These things cannot be negative. There'll also be sometimes the domain will be x, or whatever the variable is, can't be bigger than a particular number. Okay, so you are going to have to look at both the algebraic and real-world domain. So basically, this is what you're going to do. You're going to come up with the function in two variables, and remember your y quantity, whatever's on your left side of your function, is going to be the quantity you want to minimize or maximize. Decide on the domain, which is an intersection of the algebraic and real-world domain. Now, on the AP, they're going to give you this kind of a question. They're going to expect you to do all of this work by hand. In other words, you're looking for a relative max or a relative min. So what you're going to do is find the first derivative, find the critical numbers, and use the first or second derivative test to establish what the maximum and minimum points are. Now, make sure you give the answer to the question. The question could be, let's say, what is the maximum area? On the other hand, the question could be, what are the dimensions of the rectangle that will produce a maximum area? So you got to make sure you know which one of the coordinates of your max or min point you're going to use. Also, you need to give units of measure. So always reread the question before you answer it. Now, when you're doing practice problems at home, I would suggest, because these are just going to take so long, I would suggest that obviously you have to come up with the function in two variables and the correct domain. Make sure you check out the real world domain. At that point, you could either do one of two things. You could just graph the function and use the TI in that window, which is established by your domain, and actually use the TI to find the max or min. At the very least, when you're doing practice problems, feel free to use your calculator to find the critical numbers, to ask the calculator, so solve the equation, the derivative of whatever it is equals 0, and solve for x, so that you can at least find the critical numbers. Okay, this part here is review of all that we've been doing in this whole chapter. I'm hoping by now you do not have problems finding a derivative, finding critical numbers, or using the first or second derivative test to find the relative extrema. At this point, the tricky part is, can you come up with the correct equation or function in two variables? Do you know what the real world domain is? And once you get this max or midpoint, doing it all by hand or doing part of it with the calculator or all of it with the calculator, do you understand which coordinate of that max or min point is the answer to your question? And don't forget units of measure. Okay? All right. So these are questions like numbers 3 through 8. So it says find two positive numbers, I would circle that satisfy the given requirements. Okay, so we're going to do something that's like number 5. Find two positive numbers where the product is 192 and the sum of the first plus 3 times the second number is a minimum. So the thing you're trying to minimize is this famous sum right here. So let's call our two numbers, let's say x and y. Then you're going to need, the thing you want to minimize is the sum of the first plus 3 times the second. So s is what I'm trying to minimize. So s equals the first number, which I'm calling x, plus 3 times the second number, which I'm calling y. But the problem with this function is there's too many variables. That's why they gave you this piece of information. By telling you the product of the two numbers, which I've called x and y, is 192, that means, and then this is your call. You can either isolate x or isolate y here. I decided to isolate y. So y is 192 over x, and then I can come back over here and replace y by 192 over x. So it turns out here is my function. That's going to be the most important thing, is can you come up with the correct function. Now, if we were doing this by hand, and I'm going to go through this very quickly, but let's talk about domain first. And the algebraic domain is x cannot be equal to 0. The real world domain is that x has to be positive because the question said find two positive numbers. So the actual domain is x is greater than 0. If you were doing it by hand, let's rewrite s this way. There's the first derivative. There it is with a positive exponent. There it is as a single simplified factored fraction. Actually, I didn't factor it, but I didn't recognize it. When is it equal to 0? When the numerator is equal to 0, which is when x equals plus or minus 24. But remember, our domain is all positive numbers. It doesn't exist at 0, but 0 is not in the domain. Keep in mind that this limited domain will give you a number ray. So you have this one and only one critical number of 24, and etc., and you find out that there is a minimum at 24. Now remember, if it's the actual AP exam, you're going to need to show that AP justification, which means you either say f has a relative minimum at x equals 24 because f is decreasing for x between 0 and 24 and increasing for x is bigger than 24, or you can say because the first derivative of f is negative for x between 0 and 24 and positive for x greater than 24. Now, let's not forget to answer the question. The question did ask for both numbers, so we found out that x equals 24 is what gives you that famous minimum sum. So x is 24. Remember, we had established y was 192 over x, which becomes 8, and therefore the two numbers are 8 and 24. Now, you could check this. Let's say you did it on your calculator. The thing is, you're going to need a really good domain, okay? So in order to establish, because if you just do minus 10 to 10, minus 10 to 10, you'll see absolutely nothing. The one thing that's for sure is that your x component is going to be positive, because they said they were positive numbers. And obviously, if we're adding a number plus 3 times another positive number, our y's will also, our s's in this case, will also be positive. So we're only dealing with first quadrant. So you can definitely have x min 0, y min is 0. You might have to play with this a bit, and I'm suggesting here you might want to go to the table and actually go up by tens to actually watch the numbers and see that they come down and then go back up when you pass somewhere around 500. And you'll also be able to see the y values are quite big. Okay? Don't know what this is over here, but it's gone now. I don't know what that is. Delete. Okay. This is like number 12. Find the length and width of a rectangle that has an area of 100 square centimeters and a minimum perimeter. So we're going to need to find this relative minimum, but ultimately they didn't ask what is the relative what is the minimum perimeter. They're asking what are the length and width of the rectangle that will have this. Okay, so draw a picture. I called the length X and the width Y. You could call them L and W. I'm trying to minimize the perimeter, so I have P equals, of course the perimeter would be 2 times X plus Y, but that's too many variables. That's why they gave you the area, okay? So in the book, by the way, this is why I'm not doing number 12 from the book, because they couldn't come up with a number. They said A. I want to show you that. They're so pathetic. The area is A, square centimeters. Okay, well, I picked a number, 100. Okay, so area, of course, of the rectangle is X times Y. If X times Y is 100, Y is 100 over X. And now you can replace Y by 100 over X. That is your equation in 2 variables. Your domain, obviously X has to be positive. It's not going to be a negative length. And then etc. And basically, once you have the function and the domain, I'm really not interested anymore. The rest is old stuff. This is the hard part, getting the correct function and getting the correct domain. After that, you should. And that's the end of video 3.7a, part 1.